In this video we are going to go over a few concepts for physical applications of integrals. So the first one is mass. So we're going to use the formula, the mass is equal to integral from a to b of rho of x dx when the rho is the density function. So let's look at a few examples. Find the mass when rho equals 1 plus sine of x for x between 0 and pi. So the mass is equal to integral from 0 to pi of 1 plus sine of x dx. Now integral of 1 is x, integral of sine of x is negative cosine of x, evaluated from 0 to pi. So you get pi minus cosine pi minus 0 minus cosine 0. Now pi, cosine of pi is negative 1, with the negative is plus 1, and then minus 0 plus cosine of 0. So we get pi plus 1, cosine of 0 is 1 plus 1, so we get pi plus 2. Let's try and see the second problem. So this time the density function, it's a piecewise function. So the mass, it's equal to integral from, well, our x, it's between 0 and 2 and 2 to 4. So it's between 0 and 4 of rho of x dx. So let's split it in integral from 0 to 2 of 1 dx plus integral from 2 to 4 of 1 plus x dx. And I think you guys can calculate this integral, no problem. Let's take a look at another concept, the work. So the work, it's actually force times distance, but if we have a variable force, the work is given by integral from a to b of f of x dx. So let's just take a quick look at this graph. If we have a string, right, and we want to a spring, sorry, and we want to this is in equilibrium, no force applied. We want to stretch it. We can compress it, and we have no force applied to it. So let's take a look at the problem. The force is equal to k times x, where k measures the stiffness of the spring, and x is the position function, how many units we needed to compress it or stretch it. So let's take a look at problem 21. A spring on a horizontal surface can be stretched and held 0.5 meters from its equilibrium position with a force of 50 Newton. A. How much work is done in stretching the spring 1.5 meters from its equilibrium position? How much work is done in compressing the spring 0.5 meters from its equilibrium position? So let me make a quick picture. This would be the spring in equilibrium position. In part A, we want to stretch it 1.5 from its equilibrium position. So this would be 1.5. And in part B, we want to compress it 0.5 from its equilibrium position, right? This one would be the equilibrium one. Maybe make it a little bit smaller. So the force of x equals k times x. Now the force that is needed to stretch 0.5, it's equal to k times 0.5, and it's equal to 50 Newton. So from this equation, we can find that k, that constant, it's 50 divided by 0.5, which is equal to 100. So how does this help us? Well, the force now, it's actually 100x. So in part A, to find the work that we need to stretch it 1.5, it's going to be integral from 0 to 1.5 of 100x dx. So this can be quickly computed, 100x squared over 2 from 0 to 1.5, and this is equal to 112.5 joules. Let's take a look at part B. So part B is the work that needed to compress it is going to be from 0 to negative 0.5 of 100 x dx, right? Because negative 0.5, because we want to compress it 0.5. So it's going to be equal to 12.5 joules. Another type of problem is the lifting problems, and the work that we need to lift problems, it's the force times the distance. But what happens if we are lifting it at different distances, right? So we'll need integration is going to be used. So the formula that we are going to use to find the work and is going to be given by integral from 0 to a to b of rho times g times a of y times h minus y dy. And this is a general procedure where we want to lift, from example, water from a pool, right? We want to remove water from a pool, for example. So let's take a look at this problem. It says emptying a swimming pool, and we have this pool right in XYZ, and the problem says how much work is required to pump the water out of the tank when it's full. The base measures 25 meters by 15 meters, and the depth is 2.5 meters. So we want to find the work. So let's write again the formula that we saw on the other side, which is integral from a to b of rho and g of a of y, h minus y. And let's apply it for our problem. So the work is going to be integral from, so we want to remove the water, right, on this axis, right? The plane would be like every slice we want to remove it, right? We take it by slice, if you want. So then it's going to be integral from 0 to 2.5. And then rho for water, it's 1000. G is the gravity, 9.81, times a of y. So I want to find out what is the area of this slice. So that's 25 times 15. And then times h minus y. So we go step by step, right? We remove this slice, when we remove this one, and so on. So basically is this distance, which I don't know, which is 2.5, and then minus each piece. So 2.5 minus y dy. So let's do the computations. And I wrote the answer in scientific notation. 1.15 times 10 to the 7 joule. I actually rounded to 2 decimals. Let's see another concept, force and pressure. So the pressure is force over area. Now, if we are talking about hydrostatic pressure or pressure of water at rest, the force is integral from 0 to a of rho, the density of water, which we used before, times g times the a minus y times the w of y dy. So let's take a look at where do these problems come up. Well, the hydrostatic pressure on a vertical wall of a swimming pool at a depth h, and we use to find the total force that it's applied, for example, on a vertical wall such as dams. So now a minus y, this one, it's actually the depth. So it's not g of, it's g, which is the gravity, 9.81, and then a minus y is the depth, and then w of y is the width function. So let's take a look at the problem. And we actually have some steps that we want to follow. So for example, in order to solve problems like this one, find the total force on the face of the dam. So let's say this is the dam, and it has the dimension, it looks like a trapezoid. The base is 10 meters, the height is 15 meters, the top base is 20 meters, and we want to find the force, right? So what do? Draw a y-axis on the face of the dam in the vertical direction and choose a convenient origin, often taken to be the base of the dam. So I'm going to make a coordinate plane right here. This would be x, y, and the origin. And this point, for example, here is going to be of coordinates 5, 0. This point here is going to be the coordinates 10, 5. Right, just because this one is 10 now, and it goes all the way to here, so it's actually 10 to 10, 15. So now let's try to write out stuff. The force is going to be integral on the y-axis, right? So it's integral from 0 to 15 rho, that's 1000, so I'm using this formula from here. That's 1000 times g, that's 9.81, and then a minus y. So a minus y was the depth, so that would be 15 minus y, the depth, and then w of y. So let's discuss, let me pause a bit. Here I need to put something, dy. I need to put w of y. Let's discuss w of y. What is that function equal to? Well, w of y, it's the width function. So this one, I need to find out what's the equation of this. Oh, sorry, the width function. So it's this one. This is giving me the width. So how do I find that? Well, so the right slanted edge of the dam, it's a segment, is this segment, the right slanted edge of the dam. It's a segment of the line that passes through the points 5, 0 and 10, 15. So we can find the equation of the line by finding the slope. It's 15 minus 0 over 10 minus 5, so it's 15 over 5, which is 3. So now y minus, and I'm going to pick this pair, so y minus 0 equals 3 times x minus 5, so y equals 3x minus 5. Or x equals y plus 5 over 3. Or I can say x equals 1 over 3 y plus 5. So the depth will be w of y is equal to 2 times x. So it's going to be 2 over 3 y plus 5, where y is between 15 and 0. So the width of the dam is w of y is 2 over 3 y plus 5. I actually made a mistake. Y here, it's actually 3x minus 15. So x is going to be y plus 15 over 3. So plus 15. I was getting an error there, so I was wondering why. So basically, y of 0, if we calculate y of 0, we get 2 over 3 times 15, which is 10. So how wide is the dam at 0? It's 10. So we got that. And if we calculate y of 15, we get 2 over 3 times 30, we get 20, which means how wide it is at the top. So now that we found w of y, take a little bit better. So 2 over 3 y plus 15 dy.